So far, we talked about one single generator or multiple generators working together for the same pool of power. And we saw that we were not able to correct the frequency back to 60 hertz in these circumstances. So this was the closed loop that we had. This was the closed loop that we had. We made changes to the load. We saw some errors in frequency, and there was nothing we could do about it. We want that frequency to go back to 60 hertz, which means that we want this delta omega to become 0 under steady state conditions. How should we do that? Through what control input can we do that? How many inputs do we have in here? 2, right? One is here. This is the nature of the system. The load changes, okay? There's nothing we can do about it. There's one thing in here which is in our hands we can control. Do you remember what this was, the delta P reference? Where was it coming from? Yeah, the bias point, the speed changer. Here, the bias that we can give to the systems to correct the frequency. So that's what we're going to do. If you want to set the frequency back to 60 hertz or make the error 0, usually what type of action do we need to do in control systems? Integrators. You recall? Integrators tend to make the errors small or 0 under steady state conditions. So this is what we're going to do. This is called AGC, automatic generation control. So we want to automatically control the generation so that we can set the errors of frequency to 0. So remember, this is the loop that we had already. Now we would have an external loop, closing that again, taking the feedback from omega, passing it through an integrator, giving it back through the delta P reference. So integrator's job is to add up the errors, right? If you add up the errors over time, it means that you integrated the errors. If you can basically set that integral of errors over time to 0, right? Through this feedback, this means that you did the job. So this is what is going to be done. And if you simplify this block diagram, again, with the delta PL as the input and delta omega as the output, this becomes the new transfer function. And if you use the final value theorem on this, you will see that when time goes to infinity, it's as if S times this transfer function when S goes to 0, right? So that becomes delta omega under steady state conditions, that becomes 0. So through this integrator, we can basically correct the frequency back. And this is called AGC, automatic generation control. And here is a MATLAB example. In this example, we're going to use the step function. Using the step function, we want to show that the error in frequency goes to 0 after a while. And you can see that if you use these commands through MATLAB, you can show that for the system where Ki was selected to be equal to 7, then the frequency error would go to 0. And you can play around with this example, change the Ki value to different basically numbers and see how the choice of Ki can change the dynamics of this system. Under what circumstances, basically, you could get a faster response or a slower response in terms of reaching the steady state conditions. And now let's go to load frequency control in multi-area systems. So power systems are really multi-area, multiple areas that can be divided based on basically based on things such as, for example, geographical distances. And there would be, for example, Northern California, Southern California. Each of these can be assumed to be pools of power that are interconnected with one another through tie lines, transmission lines that are usually long and are basically transferring power from one side of the system to the other side of the system, one area to the other area. So this is an example of a two-area, for example, system. The two generators on the left-hand side are belonging to one area, and the two generators on the right-hand side are associated with another area. And as you can see, there are a bunch of basically lines that are connecting these two areas together. So in these multi-area systems, what you need to note is that there would be changes in the load in each area. Okay, and then because of these changes, there would be some oscillations in frequency. So, for example, in here, see that if there is a change in the frequency, then this omega, which is 377, which is 2 pi f, because of that change in the load, goes to a lesser value, and then the frequency of the system tries to go back to the same 377, but it takes a while. What you need to note is that in multi-area systems, each of the areas of the systems can be kind of simplified with a group that is belonging to a few generators in that area. So we have two groups as if, and these two groups are oscillating with respect to the other group. So if you look at basically the two generators on the left-hand side that are blue and red, you can see that the blue and red generator frequencies, it's as if it's oscillating in the reverse direction with respect to the two generators on the right-hand side, which are shown with the green and black colors, right? So this is showing basically coherent grouping of the generators. So sometimes in power system, basically analysis and control, we try to simplify the system as much as possible. So that I said, Northern California within basically with respect to the Southern California interconnected with an equivalent basically tie line. And if you make that basically simplification, you can see that based on coherency, based on the theory of coherency, which is out of the basically topic of this class, but keep that in mind. Using these coherency methods, you would be able to simplify the behavior of the system in a way that our minds in control rooms can comprehend that. Because if you do not do that, if you do not interpret the data based on these basically rules or simplifications, then there are thousands of generators that each of them is oscillating with its own frequency, and you do not understand what's going on in the system. So there must be some tools that can simplify the comprehension of all of that behavior in the system for us, and coherency is one of those methods. All right, so this was just in parentheses for you to note. These are some type of questions that could come up during your interviews. We don't go through an analytical, basically, procedure for coherency and all of that, but I just wanted you to be mindful of that and note that. So the two areas that we talked about could be simplified as two generators. Generator number 1 with E1 power angle delta 1 versus generator 2 with E2 with angle delta 2. X1 is the equivalent basically reactance of the first area. X2 is the equivalent reactance of the second area or second generator representing that area. And these two areas are interconnected with X tie, which is showing the equivalent reactance that is connecting these two areas together, okay? Now, if you just ignore losses, you can see that the power that is going to be transferred between these two areas, the P going from area 1 to area 2, can be represented as E1, E2 over X12, where X12 is the sum of these reactances, times sine of delta 1, 2, where delta 1, 2 is delta 1 minus delta 2. So the transfer of power between these two areas has something to do with the difference in the power angles. If you assume that E1 and E2 and the reactance between the two areas is remaining almost constant. So what changes the power transfer would be delta 1, 2, which is the angle difference between the two areas. Keep that in mind. And using that, basically, when you come up with, again, a linearized power flow, if you linearize the system, delta P1, 2 can be associated with PS times delta 1, 2, where delta 1, 2 would be the delta 1 minus delta 2. And this PS is called the synchronizing power coefficient, which we talked about that in the previous session also. And that would be basically the slope of the power angle curve between the two areas. So if you just go ahead and plot P1, 2 versus delta 1, 2, at steady state conditions, you would be working at this point where you can note it as delta 1, 2, 0, and the slope of that would be the PS, the slope of basically that curve. Now, if overall delta 1 would be greater than delta 2 because of a change, there are some change because of a load change, for example, or something that changes in the system because of a disturbance, there would be an angle difference between the two areas if overall delta delta 1, the changes of the angle in delta 1 is greater than delta delta 2, the changes of power angle in delta 2 in area 2, then power would be transferred from area 1 towards area 2. If that's reversed, then there would be the reverse of power from area 2 to area 1. Now, these two areas can be represented the same way that we came up with the block diagram of a single area with two block diagrams, each belonging to one area that are interconnected with one another through this PS over S. So look at here. This is representing area number 1. This is representing area number 2. And delta P12 would be representing the transfer of power from one area to the other area, the changes of the transfer power from one area to the other area through this representation. So there is a change in frequency in area 1, there is a change in frequency in area 2, and all of these together would be representing the delta P12, which is the change of power from area 1 to area number 2. All right, so if you look at this, basically you can come up with delta P12 over S, which would be PS over S times delta omega 1 minus delta omega 2 under Laplace transformation. And also you can come up with basically some kind of frequency change with respect to under steady state conditions with respect to the changes in loads in any area. Keep that in mind, even though we talked about this delta omega 1 and delta omega 2, which are the changes of the frequency in each area, under steady state conditions, all delta omega would be the same delta omega. So the whole frequency of the system, if the system is interconnected, would be one change in omega for the whole system. There would be transitions in different areas, but those transitions in frequency will all go back to the same point, which means that for the whole interconnected area, we would have one frequency, and in the end, under steady state conditions. And that we call delta omega SS delta omega under steady state conditions. Now these I's that you see in here are representing each area in the system. So if you have a multi-area system in general, you could have a delta PL, a change in the load in that area. You could have the change of mechanical power in that area. You could have a certain sensitivity of load over frequency in that area. And this delta PI underline is showing basically the change of transfer of power from that area with other areas of the system. Okay, so for example, if you have a 3-area system, let me give you a better visual representation. This is area 1, this is area 2, this is area 3, and this is the tie line between area 1 and 2, a tie line between area 2 and 3, tie line between areas 1 and 3. So you would have P12, a transfer of power from area 1 to area 2, a transfer of power from area 2 to area 3, and a transfer of power from area 3 to area 1, okay? Now, when you're talking about this delta PLI, delta PL instead of I, let's put 1, for example. If you're talking about the change in load in area number 1, that should be equal to delta PM1, the change of mechanical power in area 1, minus D1, the sensitivity of area 1 to frequency, times delta omega under steady state conditions, minus this delta PI underscore means delta P1, the changes of power from area 1 to area 2, minus the changes of power from area 1 to area 3. So that's the sigma of Pij, where j goes from basically 1 to, in general, for an n-area system, your j goes from 1 to n, where j is not equal to I, not including itself. So the transfer of power from that area towards other areas in the system. Then, based on that, you can come up with basically delta omega under steady state conditions for the whole system based on delta PL and all the D and R coefficients in different areas of the system. And delta PL in general would be basically the sum of delta PL in each area in the system. And if you call you can see that you have D1 plus 1 over R1, D2 plus 1 over R2, and so on and so forth. If you call DI plus 1 over RI as BI, and you call it the frequency bias factor, then delta omega under steady state conditions could be simplified as equation 5, okay? And you can also see that the basically change of power from area Y towards other areas can be represented as this. The sigma, these sigmas in here, pay attention to them. We are talking about an area of n generators, n equivalent generators. Each of them have their own basically B factor. Each of them have their own basically change in load. So keep that in mind. You can basically consider that to find out the change of transfer of power from that area towards other areas in the system. In the special case of two areas only, our calculations would be much simpler. So we have just one transfer of power, delta P12, from area 1 to area 2, which would be based on the changes of load in each area, area 1, as well as area 2. Let's talk about the same two-area, simple two-area system. Area 1, area 2, okay? And we have a bunch of things in each area. P mechanical in area 1, transfer of power from one area to other area. P mechanical in area 2, all right? Omega in area 1, and omega in area 2, which must be equal to omega under steady state conditions, right? So we have just one omega in the whole system. Now let's assume that also there is a PL1 and there is a PL2, load in area 1, load in area 2, okay? Now let's assume that there is a change of load in one of the areas, for example, area number 1, delta PL1, okay? Because of that change in load in area number 1, we could have changes in each of these other elements in the system that we see. So that includes a change in the mechanical power in area 1 to respond to the changes of load in area 1. The changes of mechanical power in area number 2, okay? And we assume that there was no change in load in area 2, okay? But because of that change of load in area 1, both areas will need to respond in general, and there would be a change in the transacted power between the two areas as well. And your frequency will also change. There would be a change in frequency under steady state conditions as well. So we have one change in one area that causes all of the areas in the system to respond to that, okay? Now, let's compare this with the conditions that we expect in our system based on the contracts that are existing in general between different areas of the system. So based on the market, we know that power system is working based on market. So there is a power market. Based on that market, area 1 and area 2 are going to have some transaction of power between each other. So for example, P12 is supposed to be 100 megawatts going from area 1 to area 2. All right. Now, there is a change in the load in area number 1 that could happen in any area. So for example, 10 megawatt was changed in area number 1. Based on the contract that was existing between the two areas, we were supposed to transfer 100 megawatt from area 1 to area 2. Now, because of that 10 megawatt that happened, 10 megawatt change in load that happened in area 1, instead of 100 megawatts that we were supposed to transfer from area 1 to area 2, now we're transferring 95 megawatts, for example. Is that acceptable from a power market standpoint? There is a contract between the two areas to transfer 100 megawatt. There is a change in load in area number 1. So does that have to impact the transfer of power between the two areas? Based on the power market, it shouldn't, right? Because there's money involved. You want to transfer 100 megawatt based on this amount of money from area 1 to area number 2. Now, area 1 has changed its load. Fine. Area 1 has to deal with that, not the transacted power between the two areas, not even area 2. And also, there is another problem here, and that's the changing frequency. So we don't want any of those. So there is a change in area number 1, load, fine. This has to go to 0. This has to go to 0. Area number 2 should not respond to that. Delta omega has to go to 0. There should not be a change in the frequency in the system. But these two can remain, okay? There was a change in area 1, and area 1 has to respond to that, not other areas. Just delta PM1 needs to change, right? So this is the ideal scenario that we are looking into. Under this system that I just showed you, this is not going to happen. If there is a change in load in area 1, that will impact the frequency. The frequency will have some error. Also, delta PM2 will change to respond to delta PL1. Also, the delta P12 will change. So all of these, remember, this is a linearized system, which means that all of these deltas under steady state conditions are ideally 0. All of these deltas under steady state conditions must be 0. If there is a change in load in area 1, it can change delta PM to a non-zero value, but it should not change the frequency. It should not change the delta PM2. It should not change the delta P12. Okay? So we're trying to investigate how we can do that, how we can set all the basically errors that are associated with other areas and transactions on power and frequency, all going back to 0. So this is what we call AGC, or automatic generation control in multi-area system. Remember AGC, what was AGC doing? Automatic generation control. This was AGC. AGC was this outer loop that would set the frequency error back to 0. Okay. Now, in multi-area, this was for one area only, one generator, one equivalent generator. Now, if you have multiple areas in the system, you have to do the same type of AGC for a multi-area system, which means that you have to bring basically the same integrator control for both areas. You have to feed, in order to set the error back to 0, you have to feed basically delta omega from each area through B1 and B2. And what is B? What was B? B was the frequency bias factor from each area, feed it back, and make what you call ACE signal. This is called ACE signal for area 1, and this is called ACE signal for area 2. What does ACE stand for? ACE, area control error. Exactly. So area control error for each area is going to be found based on, in general, some gain times the change of frequency in that area, plus the sigma of the changes of transacted power between that area and other areas in the system. For the case of a two-area system, that translates to ACE for area 1. And that gain that I just showed you, KI, is usually the same BI, area bias control. The optimal performance, it's been shown that if you choose that KI to be equal to BI, that would be the optimal case. So based on that, in summary, for the two-area system, we would have ACE for area number 1 would be B1 times delta omega 1 plus delta P12, and ACE for number 2 area is B2 times delta omega 2 plus delta P21, which is the same as minus delta P12. So if you're assuming that the system is lossless, that's what we assume. Delta P12 would be the negative of delta P21. So we use that. So based on that, this would be now our control loop. Okay. Now let's go to the examples with ACE and without ACE. So example number 4 is talking about a two-area system, each having their own characteristics, D1, H1. The base of power in area 1 is 1000 MVA. Tau G1, tau T1, these are associated with the time constants in the governor and turbine, basically, block diagrams in area 2. So note that, in general, we need to convert everything to the same base, the D and R values. But since here, both bases of power in the two areas are 1000 MVA, we don't have to do that. They are all under the same common base. We're saying that the system is operating at a nominal frequency of 60 hertz. The synchronizing power coefficient under steady state conditions is 2 per unit. A load change of 187.5 megawatt is happening at area 1. We want to see what happens. This system does not have the ACE signal, the area control there. All right, so we want to see the new steady state frequency deviations and the change in the tie line flow, as well as the mechanical powers in each area. And then we want to construct the system's block diagram in Simulink, and under the same figure, plot the frequency deviation response in each area. And using the simulated system in part 2, we want to plot the changes in the tie line power flow and the mechanical powers in each area on the same figure, okay? All right, so part 1 is the steady state analysis, part A. Delta PL1 was 187.5 megawatt. We divide that over 1,000 to make that in per unit because our calculations are all in per unit. Delta omega SS using the formula would be minus delta PL1 over B1 plus B2, which translates to minus 0.005 per unit, or in other words, the frequency in the new system would be 59.7 hertz. And the delta PM1 and delta PM2 would be based on the minus of delta omega SS over R1 and R2, which would become 100 megawatts and 80 megawatts. So again, going back to the fact that we had 187.5 megawatt change in load, but that has been responded by an overall 180, which is not the same 187.5. And that's because of the D values in these two areas, right? Because of these D values and the fact that these D values are not zero, then the sum of mechanical powers will not be the same as the sum of P loads. Okay, and now the transacted power change, the delta P12 would become B2 over B1 plus B2. Remember that this is the formula for the two-area system. If delta PL2 is 0, delta P12 would only depend on delta PL1. And because of that, we see that delta P12 has become minus 84.5. What that really means is that whatever was sent from area 1 to area 2 has now become 84.5 megawatts less, right? So if there was like 1,000 megawatts going from area 1 to area 2, now that value has become 1,000 minus 84.5 megawatts. Okay, now if you construct the Simulink diagram and get the plots, here is what you see. For the frequency deviations in each area, you can see that the frequency deviations for both areas was 0 pre-disturbance. Now, because of that disturbance that happened to the system, and that was the load change in area number 1, both areas will go through some transitions in frequency, but both areas would go to the same frequency in the end, because that's an integrated area between the two systems. So we go from 0 to minus 0.005 per unit. In terms of the mechanical powers and the transacted power between the two areas, we see that all of those were zeros. There was no deviation from the transacted power from area 1 to area number 2. There was no deviation in the mechanical power for area 1, neither for area 2, but these are all going through some changes. Okay, so this becomes delta PM1 in the end, this becomes delta PM2 in the end, and this becomes delta P12 in the end. So this is the system that does not use the ACE signal, does not use the AGC control, automatic generation control. So if we go ahead and use the ACE signal, automatic generation control, we would be expecting these deviations in frequency to go back to 0 again. Under steady state conditions, there would be some transitions, that's fine, but the errors in frequency will need to go back to 0 again. Also, out of these three, who should go to 0? If there is a change in load in area number 1, who should go to 0 out of these three plots? There's a change in area 1. Fine. Area 1 needs to tolerate that, which means that delta PM1 could be non-zero. But what about delta PM2 and delta P12? They would need to go back to 0. Okay? The transacted power should not change. So delta P12 should go back to 0. Delta PM2 should go back to 0 also, because there was a change in area 1, fine, but area 1 needs to deal with that. The generators in area 2 should not respond to that under steady state conditions. In transients, everything can happen, but in the end, they should go back to 0. All right, so this is example number 5, which is talking about automatic generation control in multi-area in 2 areas using 0.3 as integrator gains and including the ACE signal. So if you construct that system, you will see that what we wanted is going to happen. So there is some transition in delta omegas, but they both go back to 0. There is a transition in delta PM2, but it goes back to 0. There is a transition in delta P12, but it goes back to 0. But delta PM1 will not go back to 0, and that's because the change in the load was happening in area number 1. So somebody has to respond to that, and that's its own area, which is area number 1. So the generators in area 1 need to respond to that. Okay, so this was a summary of load frequency control in multi-area systems. Keep that in mind that also under optimal conditions, all of these. So this is we're talking about basically AGC. This AGC is happening, automatic generation control, is happening in the matter of seconds to minutes. Okay, so the first basically agents that respond to the disturbances are basically the generators through their droop controls. So that's called the primary control. Keep that in mind. We're talking about 3 types of controls. The primary, that's the droop. That's the first physical response. Because if there is a change in the load, the frequency will deviate. And the first basically objects where the energy would be released from or given to would be the inertias of your generators. If you demand more load, the easiest object would be the inertia of the generator. So the frequency drops so that it can release some power for the extra load. If load reduces, if there is a reduction in the load in the system, the first object in the system to tolerate that would be the inertia of the generator to receive that, basically absorb that extra power into itself so that the frequency boosts temporarily. Okay, so that's called basically the primary control, and that usually gets handled through the droop line that we just talked about. And then we have a secondary control, which is the same as AGC, the AGC that tries to bring back the error in the frequency to 0. And that happens within a few seconds, up to a few minutes, okay? So that's a slower. The primary control frequency control is very fast, happens instantly. But the secondary control, AGC, is happening through ACE, and it takes a few seconds for the system, up to around a minute, to respond to that. Now, in the end, we want to have basically an optimal generation in our systems, which means that the settings for the generators can happen between this hour and the other hour. So that happens within a few minutes to an hour to a few hours in the future. Those settings in the generators have to change based on what we call is a tertiary control. And that's ruled by the market and ISO, independent system operators, that command the different generators in the system to change their settings based on market. And that's a different story that goes to economics, which we talked about briefly when we talked about optimal dispatch of generation. All right, now let's go to a voltage control. So we talked about frequency, but the second important quantity in the power systems to be controlled is the voltage. And the first place where voltage is getting controlled is at the generators. So generators do get a hold of voltage using their excitation systems. So excitation is very important because it impacts the excitation current, which impacts the E, or the internal voltage in the synchronous generators, which impacts the reactive power. So reactive power, voltage control, they are hand in hand in both generation transmission systems. And frequency and active power are hand in hand. So load frequency control has a lot to do with the active power, but the voltage control has a lot to do with reactive power through the excitation systems. Here is basically what we see. We have the terminal of the generator, which we are going to sample the or get the measurement of the terminal voltage. We pass it through some potential transformer, some kind of PT, potential transformer, where it basically, that's a high voltage. We need to reduce it down, get a sample from, rectify that, okay? Because voltage is sinusoidal, right? So that's through the rectifier. We rectify that voltage after we're sensing that, and this becomes the sample of my voltage. I'm going to compare that with a reference voltage where I'm supposed to be at, and then the error would be this VE, the error in the frequency. Then in order to impact my exciter, I pass that error in the voltage through an amplifier to the excitation system to change the voltage of the exciter. And that will impact the internal voltage of my generator, which in turn will impact the terminal voltage. So this is a closed loop. As you can see, the errors in the voltage will have to basically impact the exciter to impact the terminal voltage. Now, each of these components in these closed paths have their own dynamic behavior, including these rectifier, potential transformer, excitation system, the generator itself, the amplifier. All of those have their own block diagrams, which we're going to talk briefly in here. The amplifier model is through a K of the amplifier, plus basically a tau A, which is showing the time constant of the amplifier. So typically, Ka from 10 to 100, tau A is ranging from 0.02 to 0.1 seconds. And in many cases, we can also neglect that, assuming that the amplifier model is only a gain, does not involve any delays, okay? We have the exciter model. The exciter model, in its simplest form, can be a gain with a time constant, which in many cases we can also ignore that tau E if it's very small and just approximate the exciter with a gain. The generator model has its own basically dynamics to basically impact the terminal voltage through a gain and time constant. And the sensor model, so the sensor is basically this potential transformer and the rectifier together, which would be, again, in its simplest form, like a gain and a time constant. The overall AVR block diagram becomes something like this. We're getting the VT, pass it through a sensor here, compare it with the reference, get the error in the voltage, pass it through amplifier. The amplifier will pass it through the exciter. The exciter will pass it through the VF, which would be implemented through the generator to result in VT. One thing I want you to note is that since the model of the generator and all of these components that we are considering in this loop are linear models, then we will not need to linearize the system anymore. We can directly work with the basically models as is without linearizing them. That's why you don't see deltas in here. You see the values themselves. You don't see delta V reference. You don't see basically delta VR. You don't see delta VT. These are directly the values themselves. That's because the system is linear, or at least we're assuming that it's we are approximating that with a linear system. So if you go ahead and find again the terminal voltage under steady state conditions through the final value theorem, you see that the terminal voltage under steady state conditions will depend on all of these gains, Ka, Ke, Kg, Kr, and that has been shown through this example number 6. So in this system, we call it AVR. AVR stands for automatic voltage regulator. In this AVR system, let's assume that we have Ke, tau E, Kg, tau G, Kr, tau R, and tau A. The only thing that we don't know is Ka, which is the gain of the amplifier, and we want to find out a specific range for that stable operation through the Routh-Hurwitz method, and then through the Routh-Locus method. Okay, so the Routh-Hurwitz method works based on the denominator of the closed loop, which is 1 plus kgh. If you put it in here and get basically the characteristic equation, you can come up with this table. And this table will dictate that Ka should be greater than -1 and smaller than 12.16, which practically in a physical system, gains should be positive numbers. So this means that you have to be between 0 to 12.16 as the gain of your amplifier so that you see a stable response, stable behavior in your AVR. If you go out of that range, if you go beyond 12.16, your system will not be stable. So you cannot just assume that whatever amplifier gain you want, you can put. That's not going to work. The same basically behavior or the same conclusion can come from using the root locus method with the open loop transfer function, which uses basically KGH. If you write up KGH based on the numerator and denominator, plot that using MATLAB, you see that on the imaginary axis, the critical point is associated with a gain of 12.4, which is very close to that 12.16. So this is another way that can be used to find out that gain. The steady state response is 10/11, which is 0.909. So we're commanding 1. We want the terminal voltage to be at 1 per unit, but we're getting 0.909. There is an error, right? So that error is 1 minus 0.909, which is 0.091. Remember, this is happening under Ka equal to 10. So if you assume that Ka is equal to 10, which is below 12.16, an acceptable value, you get this error of 0.091. Now, if you go ahead and plot that step response using the step function in MATLAB, here is what you see, the terminal voltage. You command 1, you get to something belower than 1, and it takes almost 20 seconds for you. And after even 20 seconds, you've not reached a steady state condition. You can see that you see some oscillations. So obviously, this is not showing a relatively stable response. So when we talk about stability, we want the system to go fast, and there would be no oscillations in the responses. Obviously, through this system of AVR that we have as of now, which includes basically the sensor amplifier, we're not getting that desired response. We have, first of all, we're not getting to a 0 error. Second of all, it takes a lot of time for us to reach that steady state condition. The ways that we can improve the performance of the AVR system, first of all, is through a rate feedback. So the rate feedback, which we call it a rate feedback stabilizer, will enhance the relative stability by adding a 0 to the AVR's open loop transfer function. And that's through here. You get from VF after the exciter, you get a sample through this stabilizer transfer function and feed it through this basically extra input to here, to this add block. So this is your stabilizer, which its transfer function would be some kind of SKF. You can see that a 0 has been added to the numerator, and that's why it tends to stabilize the system, remove oscillations faster. Again, going back to your 184. So if you're going to implement that rate feedback stabilizer to the same example that we had before with a KF of 0.4 and tau F of 0.04, you can see that you can basically plot that response, step response, and construct the block diagrams of the system, where you could construct the basically feedback control system, find the TF of the plant, the transfer function of the plant, and use the step command. So all of those steps have been shown in here. So you can see that this is going to be the response. It is much, much more stable than the response that you had before. So previously you had 20 seconds and still not steady state, but now you are taking 14 seconds and there are not much oscillations. You reach your steady state pretty much. But the problem is that voltage is not still at 1 per unit, 0.909. So still you have some error, but that error is not 0. So that error is not 0, but still at least your response is stable. So we improved. Now in the next step, we're going to use a PID controller. The PID controller is basically using a PID block, which is proportional, integral, and derivative. which is the good things about basically the derivative portion tries to stabilize the system, improve the stability. The I portion, the integral portion of that, is going to improve the steady state conditions or remove the errors under steady state conditions. That's what integrators do. Integrators tend to make the error smaller, and derivative basically controllers try to stabilize the system. So that has the good things from both worlds. And now through this example number 8, we're going to implement those KP, KI, and KD values, and we're going to see that under 2 seconds, we're able to reach the steady state response, and we're going to be perfectly at 1 per unit for the terminal voltage. So this shows you the transition also from a poor AVR to a better AVR using the rate feedback and a much better AVR using the PID control.